Imagine batteries that are 5 times as powerful as conventional lithium-ion batteries. Let's start by talking about the typical lithium-ion batteries that we use in our daily electronics. Even though they've been very helpful for humanity, there's always been a need for more potent, durable, and sustainable energy sources. However, what if I told you that there will be a significant change to the game soon? This battery is a novel form of sugar-doped battery that claims to have 5 times the capacity. What kind of battery is it, and can it live up to the hype? Come explore this innovative lithium-sulfur battery and how it has the potential to completely transform the electric vehicle market. Lithium-sulfur batteries present a viable alternative for powering our gadgets and cars in the future, in contrast to traditional lithium-ion batteries, which are costly to make and have a limited capacity. However, there are certain difficulties with lithium-sulfur batteries. The physical and chemical alterations that take place in the electrodes during charging and discharging cause them to perform poorly over time. Sulfur compounds contaminate the lithium anode, decreasing its efficiency, while the sulfur cathode has a tendency to expand and contract, resulting in damage and fissures. An innovative approach has been developed by Australian scientists to address these issues. This development may make lithium-sulfur batteries a competitive substitute for next-generation energy storage technology. Lithium-sulfur batteries have the potential to completely transform the markets for renewable energy, electric vehicles, and portable devices due to its high capacity, affordability, and environmental friendliness. The enormous energy capacity of lithium-sulfur batteries has made them an appealing option for energy storage enthusiasts and researchers. This feature has the potential to transform mainstream applications. However, ongoing stability problems have made it more difficult for them to be used widely. The building of the battery is the fundamental problem. The sulfur component in the battery experiences major changes during the charging and discharging procedures. It expands and contracts, putting the materials under a great deal of mechanical stress and ultimately accelerating their disintegration. Concurrently, sulfur compounds contaminate the lithium electrode on the other end of the battery, reducing its total performance and lifespan even further. But now these clever researchers at Melbourne's Monash University have created a unique binding agent that essentially adds more space around the sulfur particles in the battery. During the charge and discharge cycles, this clever design gives the sulfur more space to safely grow and compress. Their invention thus produced a high-capacity lithium-sulfur battery with a cycle life of more than 2,100. However, the researchers didn't end there. They focused on the other side of the problem, which is the overabundance of sulfur on the negative lithium electrode. The next major discovery has its origins in an unanticipated study from 1988 that showed how some sugar-based materials can prevent degradation in geological sediments by forming strong connections with sulfides. This new finding suggests that adding compounds derived from sugars to lithium-sulfur batteries may be able to lessen the negative electrode's contamination. By doing this, these creative scientists want to improve the stability and longevity of lithium-sulfur batteries even further, bringing us one step closer to realizing the incredible promise of this material for energy storage in a variety of contexts, such as renewable energy grids and electric automobiles. Utilizing a novel strategy in lithium-sulfur batteries, the research study sought to address a persistent problem affecting the longevity and performance of these batteries. Polysulfide leaks from the positive electrode, sometimes referred to as the cathode, is the problem at hand. Chemical compounds known as polysulfides are created when sulfur and lithium combine during the battery's charging and discharging cycles. These polysulfides have a tendency to migrate from the cathode to the anode, or the negative electrode, where they can develop growths that are troublesome and shorten the lifespan and efficiency of the battery. Polysulfide shuttling is a phenomenon that poses a significant obstacle to the advancement of lithium-sulfur batteries. The research team added a sugar-based adjuvant to the complex cathode architecture in order to solve this issue. This natural source addition, which comes from corn or sugarcane, did more than just keep the cathode materials together. It also created microstructures that looked like webs. The behavior of the problematic polysulfides was significantly regulated by these web-like structures. They served as actual physical barriers that stopped the polysulfides from moving from the cathode to the anode. Additionally, they produced chemical reactions that improved the polysulfide's electrochemical activity and stabilized them. The experimental battery demonstrated an excellent capacity of almost 700 mAh per gram of material after the addition of the sugar additive. Capacity is a measure of how much charge the battery can store per unit of mass. The fact that this excellent performance was maintained for an amazing 1,000 charging cycles, a measurement of the number of times a battery can be charged before seeing a substantial reduction in capacity, was even more impressive. This is a remarkable development in energy storage technology since it signifies a major improvement in the stability and longevity of lithium-sulfur batteries. So each charge lasts longer, extending the battery's life, says Yingyi Hang, the first author and a PhD candidate, and manufacturing the batteries doesn't require exotic, toxic, or expensive materials. Even while this research is unquestionably revolutionary, there are still several issues that must be resolved before lithium-sulfur batteries can be easily incorporated into commonplace gadgets like electric cars and cell phones. To meet the increasing demand for energy storage solutions, some of these problems include optimizing the electrode's architecture to maximize its surface area and capacity, addressing potential scalability issues, and fine-tuning the production process to assure consistency and quality. However, there are a lot of potential advantages to lithium-sulfur batteries. After overcoming these obstacles, lithium-sulfur batteries have the potential to completely transform the energy storage industry. They might dramatically increase the number of years that cell phones and electric cars can operate, as well as increase the distance that they can travel between charges. This is due to the exceptional energy density, the quantity of energy stored per unit of volume, that lithium-sulfur batteries are able to attain. Actually, according to researchers, this technology has the capacity to store energy that is 2 to 5 times greater than that of current standard lithium batteries, which are based on lithium polymer or lithium-ion chemistry. Lithium-sulfur batteries would therefore be perfect for high-power and long-range applications like electric cars, drones, or satellites. At the Bloomberg Energy Finance Summit in San Francisco, Selena Mick-Whitejack, the chief battery technology officer of startup Lightning, said a commercial lithium-sulfur battery can make electrification something that is abundant, where it's easy to electrify everything. A lithium-sulfur battery is currently being developed by Lightning. Due to the restricted supply of nickel, current lithium-ion batteries, which are widely utilized in consumer devices, electric vehicles, and grid storage, face difficulties. These batteries' positive electrodes or cathode contains nickel, which is essential for boosting energy density and lowering battery costs. But nickel is a rare and expensive metal, with social and environmental effects associated with both mining and processing. Thus, one of the main objectives of battery research is to identify substitute materials for the cathode. Another important component of lithium-ion batteries, cobalt, is a cause for concern. In order to prevent thermal runaway, a hazardous situation in which the battery overheats and catches fire, cobalt is employed to stabilize the cathode. However, the majority of the world's cobalt mining is done in the Democratic Republic of the Congo, where the industry is beset by serious human rights violations, including child labor, hazardous working conditions, and armed conflicts. In addition, cobalt is a pricey and rare metal, and there won't be enough of it to meet the rising demand for batteries. The theory behind lithium-sulfur batteries is that sulfur is cheap and plentiful, which might make these batteries less dependent on trouble spots and less expensive than the $150 per kilowatt-hour lithium-ion batteries that are now on the market. Currently, lithium-ion batteries allow electric cars to go around 300 miles between charges. However, a lithium-sulfur battery has the potential to double this distance or make an EV far lighter than a lithium-ion one. This is due to the fact that lithium-sulfur batteries possess a theoretical energy density that surpasses that of lithium-ion batteries. Currently, the key question that hangs over the battery industry is whether a business can effectively design and produce a large-scale, high-performance, reliable lithium-sulfur battery. This is an essential step in taking the promising technology from the lab to the market so that companies and consumers can use it. Although researchers, large battery firms, and startups are working on the chemistry and engineering of lithium-sulfur batteries, none are currently being produced on a large scale for commercial use. This is due to the fact that mass production cannot be viable or possible until a number of technical and economic obstacles are resolved. Scaling up the production process is one of these difficulties. Large-scale lithium-sulfur battery production necessitates specialized machinery, quality assurance, and safety precautions. Optimizing the production process is crucial in order to minimize waste, energy usage, and expenses. In addition, the production method must work with the current supply chain and infrastructure for battery manufacturing. If not, new facilities and collaborations must be formed. Maintaining constant performance and quality is another issue. The performance and durability of lithium-sulfur batteries vary greatly based on the design, materials, and production techniques employed. Therefore, strict testing, standardization, and certification are necessary to guarantee consistent quality and performance of lithium-sulfur batteries at scale. Furthermore, the operational parameters of temperature, humidity, and cycling rate affect the longevity and performance of lithium-sulfur batteries. Thus, comprehensive validation and verification are necessary to guarantee that lithium-sulfur batteries can satisfy the various demands and expectations of various applications and markets. So what are your thoughts on this? Let us know in the comments section down below. As always, thanks for watching, and we'll see you in the next video.